Physics is the most basic of the sciences. It deals with the behavior and structure of matter. The field of physics is usually divided into the areas of motion, fluids, heat, sound, light, electricity, and magnetism, and the modern topics of relativity, atomic structure, condensed matter physics, nuclear physics, elementary particles, and astrophysics. We will cover all of these topics in this book, beginning with motion, or mechanics as it is often called. But before we begin on the physics itself, let us take a brief look at how this overall activity called science, including physics, is actually practiced. The principal aim of all sciences, including physics, is generally considered to be the search for order in our observations of the world around us. Many people think that science is a mechanical process of collecting facts and devising theories. This is not the case. Science is a creative activity that in many respects resembles other creative activities of the human mind. Let's take some examples to see why this is true. One important aspect of science is observation of events. But observation requires imagination, for scientists can never include everything in a description of what they observe. Hence, scientists must make judgments about what is relevant in their observations. As an example, let us consider how two great minds, Aristotle and Galileo, interpreted motion along a horizontal surface. Aristotle noted that objects given an initial push along the ground, or on a tabletop, always slow down and stop. Consequently, Aristotle believed that the natural state of an object is to be at rest. Galileo, in his re-examination of horizontal motion in the early 1600s, imagined that if friction could be eliminated, an object given an initial push along a horizontal surface would continue to move indefinitely without stopping. He concluded that for an object to be in motion was just as natural as for it to be at rest. By inventing a new approach, Galileo founded our modern view of motion, and he did so with a leap of the imagination. Galileo made this leap conceptually without actually eliminating friction. Observation and careful experimentation and measurement are one side of the scientific process. The other side is the invention or creation of theories to explain and order the observations. Theories are never derived directly from observations. They are inspirations that come from the minds of human beings. For example, the idea that matter is made up of atoms, the atomic theory, was certainly not arrived at because someone observed atoms. Rather, the idea sprang from creative minds. The theory of relativity, the electromagnetic theory of light, and Newton's law of universal gravitation were likewise the result of human imagination. The great theories of science may be compared as creative achievements with great works of art or literature. But how does science differ from these other creative activities? One important difference is that science requires testing of its ideas or theories to see if their predictions are borne out by experiment. Although the testing of theories can be considered to distinguish science from other creative fields, it should not be assumed that a theory is proved by testing. First of all, no measuring instrument is perfect, so exact confirmation cannot be possible. Furthermore, it is not possible to test a theory for every possible set of circumstances. Hence, a theory can never be absolutely proved. In fact, theories themselves are generally not perfect. A theory rarely agrees with experiment exactly within experimental error in every single case in which it is tested. Indeed, the history of science tells us that long-held theories are sometimes replaced by new ones. The process of one theory replacing another is an important subject in the philosophy of science. We can discuss it here only briefly. A new theory is accepted by scientists in some cases because its predictions are quantitatively in much better agreement with experiment than those of the older theory. But in many cases, a new theory is accepted only if it explains a greater range of phenomena than does the older one. Copernicus's sun-centered theory of the universe, for example, was originally no more accurate than Ptolemy's earth-centered theory. For predicting the motion of heavenly bodies, sun, moon, planets, for example, was no more accurate than Ptolemy's Earth-centered theory for predicting the motion of heavenly bodies. But Copernicus's theory had consequences that Ptolemy's did not, such as predicting the moon-like phases of Venus. A simpler and richer theory, one which unifies and explains a greater variety of phenomena, is more useful and beautiful to a scientist. In this aspect, as well as quantitative agreement, plays a major role in the acceptance of a theory. An important aspect of any theory is how well it can quantitatively predict phenomena, and from this point of view, a new theory may often seem to be only a minor advance over the old one. For example, Einstein's theory of relativity gives predictions that differ very little from the older theories of Galileo and Newton in nearly all everyday situations. Its predictions are better mainly in the extreme case of very high speeds close to the speed of light. In this respect, the theory of relativity might be considered as mere fine-tuning of the older theory, but quantitative prediction is not the only important outcome of a theory. Our view of the world is affected as well. As a result of Einstein's theory of relativity, for example, our concepts of space and time have been completely altered, and we have come to see mass and energy as a single entity via the famous equation E equals mc squared. Indeed, our view of the world underwent a major change when relativity theory came to be accepted. For a long time, science was more or less a united whole known as natural philosophy. Not until the last century or two did the distinctions between physics and chemistry and even the life sciences become prominent. Indeed, the sharp distinction we now see between the arts and the sciences is itself but a few centuries old. It is no wonder, then, that the development of physics has both influenced and been influenced by other fields. For example, the textbooks of Leonardo da Vinci, the great Renaissance artist, researcher, and engineer, contain the first references to the forces acting within a structure, a subject we consider as physics today. But then, as now, it has great relevance to architecture and building. Early work in electricity that led to the discovery of the electric battery and electric current was done by an 18th century physiologist, Luigi Galvani. He noticed the twitching of frogs' legs in response to an electric spark, and later that the muscles twitched when in contact with two dissimilar metals. At first, this phenomenon was known as animal electricity, but it shortly became clear that electric current itself could exist in the absence of an animal. Later, in the 1930s and 1940s, a number of scientists trained as physicists became interested in applying the ideas and techniques of physics to problems in microbiology. Among the most prominent were Max Delbruck and Erwin Schrödinger. They hoped, among other things, that studying biological organisms might lead to the discovery of new, unsuspected laws of physics. Alas, this hope has not been realized, but their efforts helped give rise to the field we now call molecular biology, which has resulted in a dramatic increase in our understanding of the genetics and structure of living beings. You do not have to be a research scientist in, say, medicine or molecular biology to be able to use physics in your work. A zoologist, for example, may find physics useful in understanding how prairie dogs and other animals can live underground without suffocating. A physical therapist will do a more effective job if aware of the principles of center of gravity and the action of forces within the human body. A knowledge of the operating principles of optical and electronic equipment is helpful in a variety of fields. Life scientists and architects alike will be interested in the nature of heat loss and gain in human beings and the resulting comfort or discomfort. Architects themselves may never have to calculate, for example, the dimensions of the pipes in a heating system or the forces involved in a given structure to determine if it will remain standing. But architects must know the principles behind these analyses in order to make realistic designs and to communicate effectively with engineering consultants and other specialists. From the aesthetic or psychological point of view, too, architects must be aware of the forces involved in a structure for instability, even if only illusory can be discomforting to those who must live or work in the structure. Indeed, many of the features we admire in the architecture of the past 3 millennia were introduced not for their decorative effect, but rather for practical purposes. The development of the arch was as a means to span a space and at the same time support a heavy load will be discussed in Chapter 9, where we will see that the pointed or Gothic arch was not originally a decorative device, but a technological development of considerable importance. The list of ways in which physics relates to other fields is extensive. In the chapters that follow, we will discuss many such applications as we carry out our principal aim of explaining the basic physics. When scientists are trying to understand a particular set of phenomena, they often make use of a model. A model, in the scientific sense, is a kind of analogy or mental image of the phenomena in terms of something we are familiar with. One example is the wave model of light. We cannot see waves of light as we can water waves, but it is valuable to think of light as if it were made up of waves because experiments indicate that light behaves in many respects as water waves do. The purpose of a model is to give us an approximate mental or visual picture, something to hold on to when we cannot see what actually is happening. Models often give us a deeper understanding. The analogy to a known system, for instance, water waves in the above example, can suggest new experiments to perform and can provide ideas about what other related phenomena might occur. You may wonder what the difference is between a theory and a model. Sometimes the words are used interchangeably. Usually, however, a model is relatively simple and provides a structural similarity to the phenomena being studied, whereas a theory is broader, more detailed, and can give quantitatively testable predictions, often with great precision. Sometimes, as a model is developed and modified and corresponds more closely to experiment over a wide range of phenomena, it may come to be referred to as a theory. The atomic theory is an example, as is the wave theory of light. Models can be very helpful, and they often lead to important theories, but it is important not to confuse a model or a theory with the real system or the phenomena themselves. Scientists give the title law to certain concise but general statements about how nature behaves. That energy is conserved, for example. Sometimes the statement takes the form of a relationship or equation between quantities, such as Newton's second law, F equals ma. To be called a law, a statement must be found experimentally valid over a wide range of observed phenomena. In a sense, the law brings a unity to many observations. For less general statements, the term principle is often used, such as Archimedes' principle, where to draw the line between laws and principles is, of course, arbitrary and therefore is not always completely consistent. Wow, what a typo. It says, and there is not always complete consistency. Oh, wait, that's not a typo. Scientific laws are different from political laws in that the latter are prescriptive. They tell us how we ought to behave. Scientific laws are descriptive. They do not say how nature should behave, but rather are meant to describe how nature does behave. As with theories, laws cannot be tested in the infinite variety of cases possible, so we cannot be sure that any law is absolutely true. We use the term law when its validity has been tested over a wide range of cases and when any limitations in the range of validity are clearly misunderstood. Even then, as new information comes in, certain laws may have to be modified or discarded. Scientists normally do their work as if the accepted laws and theories were true, but they are obliged to keep an open mind in case new information should alter the validity of any given law or theory. In the quest to understand the world around us, scientists seek to find relationships among the various physical quantities they observe and measure. We may ask, for example, in what way does the magnitude of a force on an object affect the project's speed or acceleration? Or by how much does the pressure of gas in a closed container, such as a tire, change if the temperature is raised or lowered? Scientists normally try to express such relationships quantitatively in terms of equations whose symbols represent the quantities involved. To determine or confirm the form of a relationship, careful experimental measurements are required, although creative thinking also plays a role. Accurate measurements are an important part of physics, but no measurement is absolutely precise. There is an uncertainty associated with every measurement. Uncertainty rises from different sources. Among the most important, other than blunders, are the limited accuracy of every measuring instrument and the inability to read an instrument beyond some fraction of the smallest division shown. For example, if you were to use a centimeter ruler to measure the width of a board, the result could be claimed to be accurate to about 0.1 centimeter, the smallest division on the ruler. The reason is that it is difficult for the observer to interpolate between the smallest divisions, and the ruler itself may not have been manufactured or calibrated to an accuracy very much better than this. When giving the result of a measurement, it is also important to state the precision or estimated uncertainty in the measurement. For example, the width of a board might be written as 5.2 plus or minus 0.1 centimeters. The plus or minus 0.1 centimeters represents the estimated uncertainty in the measurements, so that the actual width most likely lies between 5.1 and 5.3 centimeters. The percent uncertainty is simply the ratio of the uncertainty to the measured value multiplied by 100. For example, if the measurement is 5.2 and the uncertainty about 0.1 centimeters, the percent uncertainty is 0.1 over 5.2 times 100, equaling 2%. Often, this uncertainty in a measured value is not specified explicitly. In such cases, the uncertainty is generally assumed to be 1 or 2 units, or even 3. And the last digit specified, is generally assumed to be 1 or 2 units, or even 3, in the last digit specified. For example, if a length is given as 5.2 centimeters, the uncertainty is assumed to be about 0.1 centimeters or perhaps 0.2 centimeters. It is important in this case that you do not write 5.20 centimeters, for this implies an uncertainty on the order of 0.01 centimeters. It assumes that the length is probably between 5.19 centimeters and 5.21 centimeters, when actually you believe it is between 5.1 and 5.3 centimeters. The number of reliably known digits in a number is called the number of significant figures. Thus, there are 4 significant figures in the number 23.21 and 2 in the number 0.062 centimeters. The zeros in the latter are merely placeholders that show where the decimal point goes. The number of significant figures may not always be clear. Take, for example, the number 80. Are there 1 or 2 significant figures? If we say it is about 80 kilometers between 2 cities, there is only 1 significant figure, the 8, since the 0 is merely a placeholder. If it is 80 kilometers within an accuracy of 1 or 2 kilometers, then the 80 has 2 significant figures. If it is precisely 80 kilometers measured to within plus or minus 0.1 kilometers, then we write 80.0 kilometers. When making measurements or when doing calculations, you should avoid the temptation to keep more digits in the final answer than is justified. For example, to calculate the area of a rectangle 11.3 centimeters by 6.8 centimeters, the result of multiplication would be 76.84 centimeters squared. But this answer is clearly not accurate to 0.01 centimeters squared since, using the outer limits of the assumed uncertainty for each measurement, the result could be between 11.2 times 6.7 equaling 75.04 centimeters squared and 11.4 times 6.9 equals 78.66 centimeters squared. At best, we can quote the answer as 77 centimeters squared, which implies an uncertainty of about 1 or 2 centimeters squared. The other two digits in the number 76.85 centimeters squared must be dropped since they are not significant. As a general rule, the final result of a multiplication or division should have only as many digits as the number with the least number of significant figures used in the calculation. In our example, 6.8 centimeters has the least number of significant figures, namely 2. Thus, the result, 76.84 centimeters squared, needs to be rounded off to 77 centimeters squared. Similarly, when adding or subtracting numbers, the final result is no more accurate than the least accurate number used. For example, the result of subtracting 0.57 from 3.6 is 3.5 and not 3.03. Keep in mind that when you use a calculator, that all the digits it produces may not be significant. When you divide 2.0 by 3.0, the proper answer is 0.67 and not 0.6 repeating. Digits should not be quoted or written down in a result unless they are truly significant figures. However, to obtain the most accurate result, it is good practice to keep an extra significant figure or two throughout a calculation and round off only in the final result. Note also that calculators sometimes give too few significant figures. For example, when you multiply 2.5 times 3.2, a calculator may give the answer as simply 8, but the answer is good to 2 significant figures, so the proper answer is 8.0. It is common in science to write numbers in powers of 10, or exponential notation. For instance, 36,900 as 3.69 times 10 to the fourth power, or 0.0021 as 2.1 times 10 to the negative 3 power. One advantage of exponential notation is that it allows the number of significant figures to be clearly expressed. For example, it is not clear whether 36,900 has 3, 4, or 5 significant figures. With exponential notation, the ambiguity can be avoided. If the number is known to an accuracy of 3 significant figures, we write 3.69 times 10 to the fourth power. But if it is known to 4, we write 3.690 times 10 to the fourth. The measurement of any quantity is made relative to a particular standard or unit, and this unit must be specified along with the numerical value of the quantity. For example, we can measure length in units such as inches, feet, or miles, or in the metric system in centimeters, meters, or kilometers. To specify that the length of a particular object is 18.6 is meaningless. The unit must be given, for clearly 18.6 meters is very different from 18.6 inches or 18.6 millimeters. The first real international standard was the meter, abbreviated M, established as the standard of length by the French Academy of Sciences. In the 1790s, in a spirit of rationality, the standard meter was originally chosen to be 1/10,000,000th of the distance but from the Earth's equator to either pole, and a platinum rod to represent this length was made. This turns out to be very roughly the distance from the tip of your nose to the tip of your longest finger, with arm and hand stretched out horizontally. In 1889, the meter was defined more precisely as the distance between two finely engraved marks on a particular bar of platinum, iridium alloy. In 1960, to provide greater precision and reproducibility, the meter was redefined as 1,650,763.73 wavelengths of a particular orange light emitted by the gas krypton 86. In 1983, the meter was again redefined, this time in terms of the speed of light, whose best measured value in terms of the older definition of the meter was 299,792,458 meters per second, with an uncertainty of 1 meters per second. The new definition reads, the meter is the length of path traveled by light in vacuum during a time interval of 1 over 1 something over 299,792,458 of a second. Okay. British units of length, inch, foot, mile, are now defined in terms of the meter. The inch is defined as precisely 2.54 centimeters. Centimeter is 0.01 meters. So, yep. Other conversion factors are given in the table on the inside of the front cover of this book, okay? The standard unit of time is the second. For many years, the second was defined as 186,400th of a mean solar day. The standard second is now defined more precisely in terms of the frequency of radiation emitted by cesium atoms when they pass through two particular states. Specifically, 1 second is defined as the time required for 9,192,631. 9,192,631,770 periods of this radiation. There are, of course, precisely 60 seconds in 1 minute and 60 minutes in 1 hour. Note that these two factors of 60 are definitions and hence have an indefinite number of significant figures. The standard unit of mass is the kilogram. The standard mass is a particular platinum iridium cylinder kept at the International Bureau of Weights and Measurements near Paris, France, whose mass is defined as exactly 1 kilogram. A range of masses is presented in that table. Okay. Enough tables. When dealing with atoms and molecules, the unified atomic mass unit is usually used in terms of the kilogram. One unified atomic mass unit specifically, equals 1.6605 times 10 to the negative 27th power kilograms. The definition of other standard units for other quantities will be given as we encounter them in later chapters. In the metric system, the larger and smaller units are defined in the multiples of 10 from the standard unit, and this makes calculations particularly easy. Thus, 1 kilometer is 1,000 meters, 1 centimeter is 1/100th of a meter, 1 millimeter is 1,000th of a meter, or 1/10th of a centimeter, and so on. The prefixes centi, kilo, and others are listed in, okay, there's a table that they're listed in. And the prefixes can be applied not only to units of length, but to units of volume mass or any other metric unit. For example, a centiliter is 1/100th of a liter, and a kilogram is 1,000 grams. When dealing with the laws and equations of physics, it is very important to use a consistent set of units. Several systems of units have been in use over the years. Today, the most important is the Système International, French for International System, which is abbreviated SI. In SI units, the standard of length is the meter, the standard for time is the second, and the standard for mass is the kilogram. This system used to be called the MKS, millimeter kilogram second system. The second metric system is the CGS system, in which the centimeter, gram, and second are the standard units of length, mass, and time, as abbreviated in the title. The British engineering system takes as its standards the foot for length, the pound for force, and the second for time. SI units are the principal ones used today in scientific work. We will therefore use SI units almost exclusively in this book, although we will give the CGS and British units for various quantities when introduced. How much is left of this? That's all she wrote. Learn about converting units after I take a snack. Jesus.